Hi. After discussing some inductive bias that we decided to introduce to neural networks such that they can handle sequence, we will now continue with the backpropagation through time. So basically the algorithm for computing gradients in recurrent neural networks. Before going into further detail, I think it's actually quite illuminating to check what is the difference between recurrent neural networks and multi-layer perceptrons. So, like if you abstract a bit your mind, the main difference is that with recurrent neural networks, you got layered shared parameters. So every time step has the same parameters, it uses the same parameters to compute activations and so on. While with MLPs, you got layer-specific parameters. Other than that, there are very little other differences. You just need to switch your mind from, going from time steps to going to layers. Of course, recurrent networks have potentially infinite time steps, as we saw, but this is not important regarding the actual architecture of the neural network. So regarding the two architectures, they're very similar. They both comprise, for this three-step or three-layer example, they comprise three modules, right? Here and here. They receive some input here. Sorry for that. Whereas MLP also normally receives input only in X, but it can also receive inputs, vertically. There is no big problem with that. So all in all, the architecture actually looks very similar. Now the question is there a difference in actual training, since there are similarities? So many similarities. Well, in many ways the training is similar in the sense that we still can use backpropagation. Nothing really changes. The only difference is that because we've got shared parameters through time, so the parameters are the same for different time steps, our backpropagation also specializes such that it handles time and shared parameterization. So we've got backpropagation through time. Now, backpropagation through time is basically the chain rule again, and our focus is on computing the gradients regarding our three parameters. So the gradient of the loss with respect to the output parameters, the memory parameters, and the input parameters. Other than that, it's exactly the same algorithm. It's chain rule, the same mathematics. One caveat, something that makes things a bit more complicated, is that because we have shared computations, the chain rule becomes a bit more involved. So this recurrency together with the shared parameterization means that we have to take some extra factors into account. So specifically, the gradients, as we'll see soon, they do not flow from a single path like in MLP. So in MLPs, you still have dependencies, indirect dependencies across layers. However, as we'll see now, when it comes to backpropagation through time, the dependencies are more direct and explicit. One potential problem in considering all these things intuitively is that the recurrence in the chain rule actually hides multiple dependencies in it. So because of writing things down, writing the equations in a very compact form, the disadvantage is that we're sort of hiding these extra connectivities, and this might cause some trouble. So now let's try to actually figure this out. We have now the unfolded graph. We saw it like in the previous sub-lecture, and we have here our recurrent neural activations, equations. Basically, it's our output equation given our current state. Our current state is computed on the basis of a nonlinearity, which receives as input the the network input and the previous state, and the previous state is basically computed again from the same equation, but one time step back. And of course we can continue this until S0. Right, so this is the unfolded graph for a recurrent neural network. And if we are to compute now the gradients with respect to the memory parameters W here are derived by the chain rule as follows here. So we take the derivative of the loss with respect to the output, then the derivative of the output with respect to the current state ST, and then the derivative of the current state with respect to the parameters W that influence that state. For the parameters of the input, we repeat exactly the same process. So the derivative of the loss with respect to the output, then of the output with respect to the state, and then of the state with respect to the parameters of the input. So these guys here. And last, for the parameters with respect to the output parameters, then the chain rule is a bit simpler. So we take the derivative of the loss with respect to the output times the derivative of the output with respect to the output parameters. Now, what is interesting here is, which terms are interesting here regarding recurrence are, these guys here and here, because they involve two variables, st and w, and st and u, and these variable w and u are actually influenced and influencing these same state variables through time. So these are the problematic terms in a way. So now let's try to figure out how we compute these problematic terms. So the derivative of the state with respect to either w or input parameters. So here w. Let's start with the memory parameters. It's a bit more, yeah. Let's start with that in the unfolded graph. So we've got the dependencies from the current, state at the time step t. And what we do, one thing we can actually think about it is that we express we express the current state of our system as a function of all previous states. We specifically assign a new state variable per time step, including the t time step, right? So this is actually quite straightforward. It's just a different way to express our function. So there is no obvious recurrency in h. However, there is a recurrency by introducing the individual state variables. Now, what is the benefit of that? The benefit of that is that it makes very clear where does the gradient flow come from. So all the gradient path flows exist from S, so our current, our output variable, to every. So there exists one gradient path flow for every connection of the output and our variable of interest W. So if there is a path via ST, we count it. We count in. If there is one more path through ST minus 1, we also count it, and so forth. And then we obtain the final derivative by summing up all the contributions. So we're summing all the gradients from all possible paths leading to a connection. And this is simply written as a sum of the derivative of S with respect to the internal state variable SI, and then derivative of SI with respect to dW. Now, if we were to write these things in terms of computational graphs, we can see it here. So we've got here initially S0, which then is multiplied by W here, and then transformed by H. This yields the S1 variable, which again is multiplied by W and then transformed by H to arrive to S2. And then the final state S is basically the outcome of all together. So the outcome of all the operations all together. So basically at the end S equals S2. Now to compute the derivative of the state with respect to the W parameter, we perform this summation as we saw here. Now the first term includes a derivative of S with respect to S2, and since this is basically the same quantity, this goes to 1, right? And the final term contains a derivative of S0 with respect to W, and S0 does not depend anymore on W. It's our very initial state. It's how we initialize things, so it's a constant and it goes to 0. So what remains is this sum. Of course, this is for the special case of 2 time steps. When you've got t time steps, you have to take into account all possible derivatives. Now, the gradient flow here flows through all the possible paths from S to W. So there is one path like there is a direct path from S2 to W, so this would correspond to this guy here, and there is also an indirect path from here, and this corresponds to the second term. Now, what is good with this formulation is that it makes very clear what are the connections of S2, so all the paths from S2 and to W. What we can do also instead is to compute the gradients with the standard change of variable differentiation. So we treat the function as, it's a nested function, it's a recurrent function. So we can just take the change of variable as per usual. We will obtain the same result, but it's a bit more involved. We have to take, to make some mental notes. For instance, we have to treat the nonlinearity H as literally a single function which receives a input, a variable like z1, without having to unfold it further. So no recursion for that, like for our computations. And by doing so, we can arrive at exactly the same results. I have written this thing down here. I'm not going to go into detail for the sake of time. However, as you can see, we arrive at exactly the identical result. It's a bit more involved though. Here we have a single equation that basically describes the process. One extra thing here for this way of deriving the gradient. Here I used the specific equations that govern the RNN, whereas in this example where I'm computing the gradient as a sum of individual internal variables, this is a general formulation. So I haven't really used specific expressions for H or for what ST minus 1 stands for and so forth. So putting everything together, we arrive at this result. So we've got again the derivative of the loss with respect to output, then of the output with respect to the state variable, and then of the state variable with respect to each of the internal state variables. And this is summation as we just saw before. And then in the end, each of these internal state variables with respect to W. And since this orange term guy here is a product as we just saw. And this orange term here is basically, we can still do one more round of chain ruling to make it simpler from st to st minus 1, t minus 1 to t minus 2, and so forth. And then we arrive here a product of Jacobians. Now, if you have a new loss per time step, we have to sum over all of them to obtain the final gradient, and we repeat exactly the same input, the same thing, like the same procedure for our input parameters. So our input parameters are also derived with the same process. Now, these equations look a bit daunting. However, you can think of it as follows. The extra terms that the RNN are, the extra complications that we have are because of these guys here. The extra terms from the past connecting the current state with our parameters W. So these are the indirect paths that yield extra gradients. If we didn't have a recurrency, then we would stick to the original first term as per our gradient. So our recurrent network adds simply extra paths to our computational graph. For our output parameter, the backpropagation is a bit simpler. The reason is that yt is equals softmax of v times st, and then there is no relation between v and st, no further relation, right? So in other words, there is no t minus 1 index involved in this equation. So this means that our gradient is simpler to compute. There are no recurrences here, and you can also see this from the graph. So our v parameter here stops before the actual recurrence happens, right? And again, if we have one loss per time step, then we have to add them all. Since, as we saw, unrolling infinitely can be a problem, in practice, I'm not sure it's actually even feasible most of the times. What one can do is truncate. That's a usual, popular strategy. You can truncate for a maximum length, and then you simply replace then the t of truncation instead of t in the previous equation, nothing else. This sort of puts more focus on the short terms, right? Which is not necessarily a bad thing, as we explained, in the sense that quite often the long terms should be ignored, right? Like, for instance, when I'm translating a sentence, I don't really need to, if I'm translating a sentence in the 200th page of a book, I don't really need to have the first page of sentences to perform a good translation. Some context is required, but that's it. So ignoring the long term is not necessarily a bad idea. However, that said, we do have some bias now introduced towards simpler models with short-term dependencies. So that's something to keep in mind. Some challenges with backpropagation with through time is, of course, the vanishing and exploding gradients, as we saw in the previous lecture for deep convolutional neural networks. Again, a recurrent network can be seen as basically an MLP with infinitely many layers and shared parameters. So basically, vanishing and exploding gradients are a persistent problem here also. Also, there is a misalignment between the gradient computations and the weight updates because of the whole recurrence situation. And another challenge, or at least in theory, is that we introduce bias due to truncation. As we saw, we explained last time, in the previous lecture, what is vanishing and what is an exploding gradient. Now, if we rewrite here the equation for our gradients with respect to the memory parameters, it's very easy to figure out that this product of Jacobians is the culprit. Very similar to what we discussed in the previous lecture. If these Jacobians, they've got spectral norms that are actually smaller than 1, then we have vanishing gradients, otherwise we'll have exploding gradients. And with vanishing gradients, as we explained, we obtain an exponentially smaller contribution. and this is for our, in the context of convolutional neural networks, that was for the very early layers, and now it's for our very early, very long-term components in our data sequence. So what it means then is that with backpropagation through time on a standard recurrent network, the model learns to emphasize the shorter terms, like what is actually closer to the present. Now, we explained that ignoring the very distant past is not necessarily a bad thing, but the thing is that because of this exponential nature, this ignoring can be actually quite quick. So it's, we do want to ignore or not take into account our very distant past, but this doesn't mean that ignoring our somehow recent past is a good thing. Like sometimes or quite often it's very important to keep some knowledge of our recent past. Regarding the exploding gradients, one popular frequent solution is to rescale the gradients, which is very simple. You compute the gradient, then you take its unit version. Basically, you normalize it with its length. You take the same gradient, in the same direction, but with unit length, and then you multiply it by gamma, so that you set the maximum size, the maximum length of your gradient. The intuition of why this helps is shown in this picture. So without clipping, you might go very far away from your actual, you might jump a cliff. But with clipping, you help the model make smaller steps and then arrive at the correct minimum here. So this works, this solution works, because intuitively you can think that exploding gradients is nothing else but an optimization issue. So just because we start multiplying big numbers, then we obtain a very big gradient that can cause problems when optimizing, when updating our weights. However, we cannot apply the same strategy of rescaling for vanishing gradients, because for vanishing gradients the problem is not an optimization issue. We don't have an optimization issue. Here we have a gradient accuracy issue. So the thing is that when you've got vectors with so small lengths, so small norms, you don't even have a real vector anymore. The direction of the vector is sort of random, because the entries, the numerical entries in your gradient are on par with your numerical accuracies of your of your computer. So even if you rescale that gradient might actually point to a very wrong direction. In any case, rescaling still focuses on short terms first, right? This doesn't change. The problem of misaligning gradients and weights is sort of it's a subtle one. So the thing is that for every step, we use different versions of variables over time. So let's say that we're at time step t here. We use the weights that we have at this moment, at this moment of time, after t time steps of updates, and then we multiply these weights with our previous state to obtain our new state. And now we go to the next, right. Based on this computation, this forward propagation, we then perform in a half step extra, we perform a backward propagation, and we update our weights to be WT plus 1. Now, in our next time step t plus 1, we use the previously computed state st with our new weights. However, we see a discrepancy because this state here was actually computed using our previous version of the weights, not the new ones. So there is a discrepancy between st and wt plus 1. They are computed with one time step difference, and well, that is introducing some sort of a misalignment that could potentially cause problems. One way we can alleviate this is by performing fewer updates. However, this might slow training. I'm not saying that this is going to be a huge problem, but it is something that you have to keep in mind. And as we explained before, in practice what we often do is that we truncate our sequences at a maximum length. So of course if it's shorter, that's okay, but it shouldn't go longer than a particular number of time step. Now, why is that a problem? Because obviously we don't compute the full gradient, we compute the gradient up to that truncation point, and this means that we don't really have the real gradient, we've got an approximation of the gradient. Does this really matter much? Well, in practice and for many applications it doesn't really matter much. I mean, after all, it's hard to anyways figure out what would be the perfect gradient, and as we have seen before, a perfect gradient is not necessarily something that we should strive for or spend too much energy for. However, and from a theoretical point of view and from a model point of view, it would be nice to have our model choose when to stop rather than us having this as a hyperparameter. Thank you.